You think gravity pulls things down. You think it's a force that attracts massive objects to each other. The Earth pulls on you, you pull on the Earth. Simple, intuitive, completely wrong. Gravity doesn't pull. Gravity doesn't attract. Gravity is not a force at all. Gravity is the curvature of space-time itself. And the reason you fall when you jump is not because Earth is pulling you down. It's because Earth is bending time, not space. Time. The flow of time itself is warped by mass and energy, and that warping is what you experience as gravity. I'm Leonard Susskind, and I've spent 50 years thinking about Einstein's general relativity. And the single most profound insight Einstein gave us, the idea that changed everything, is that gravity is geometry. Mass and energy curve space-time, and objects moving through curved space-time follow paths that look like they're being pulled by a force. But there's no force. There's only curvature. And the dominant effect, the reason you're sitting in your chair right now instead of floating away, is not that space is curved. It's that time is curved. Let me show you why. Let's start with what Einstein actually said. In 1915, Einstein published his field equations of general relativity. These equations relate the curvature of space-time to the distribution of mass and energy. The left side of the equation describes geometry, how space-time curves. The right side describes matter and energy. The equation says matter tells space-time how to curve, and curved space-time tells matter how to move. This is radically different from Newton's picture. In Newton's theory, space is a fixed background, an absolute stage where physics happens. Gravity is a force, an attraction between masses that acts instantaneously across any distance. In Einstein's theory, space-time is dynamical. It's a flexible fabric that bends and warps. Gravity is not a force reaching across space. It's the shape of space-time itself. When you drop a ball, it's not being pulled downward by an invisible force. It's following the straightest possible path through curved space-time, a geodesic, and that path happens to curve toward Earth because Earth has warped space-time around it. Now, here's the part that nobody tells you. The reason objects fall, the reason you feel weight, the reason planets orbit stars, almost all of this is due to time curvature, not space curvature. Yes, mass curves space, but the effect is tiny at everyday scales. The spatial curvature around Earth is negligible. If you drew a diagram of space around Earth, it would look almost perfectly flat. You'd need incredibly sensitive instruments to detect the spatial curvature, but the time curvature is huge. Time runs slower in a gravitational field. The deeper you are in the field, the slower your clock ticks compared to a clock far away. This is called gravitational time dilation. And this time dilation is what creates almost all of what we perceive as gravity. Let me explain how this works. Imagine you're standing on Earth's surface. Your head is slightly farther from Earth's center than your feet. This means your head is in a slightly weaker gravitational field than your feet. And because gravity bends time, time runs slightly faster at your head than at your feet. The difference is incredibly small, about 1 part in 10 to the 16, but it's real and measurable. Atomic clocks can detect this difference. Now suppose you try to throw a ball straight up. The ball leaves your hand, moving upward. But as it rises, it's moving into regions where time runs faster. Different parts of the ball, the top and bottom, are experiencing slightly different rates of time. The top of the ball is moving through time slightly faster than the bottom. This difference in the flow of time causes the ball's trajectory to curve downward. This is why the ball falls. Not because there's a force pulling it, but because it's moving through a region where time itself is curved. This sounds bizarre, but it's exactly what general relativity says, and we verified it. In 1971, Joseph Hoffley and Richard Keating flew atomic clocks around the world on commercial airplanes. When they compared the clocks to ones left on the ground, they found the traveling clocks had ticked slightly more because they were at higher altitude in a weaker gravitational field where time runs faster. The predictions of general relativity were confirmed to within experimental error. GPS satellites orbit at about 20,000 kilometers altitude. At that height, time runs about 45 microseconds per day faster than on Earth's surface. If we didn't account for this time dilation, GPS coordinates would drift by about 10 kilometers per day. Your GPS wouldn't work. The only reason it does work is because engineers program the satellites to account for gravitational time dilation. They slow down the satellite clocks to compensate. This is not theoretical. This is practical engineering based on Einstein's insight that gravity bends time. Let me give you the mathematical reason why time curvature dominates over space curvature. In general relativity, the path of an object is determined by the metric, the mathematical object that describes the geometry of space-time. The metric has components that describe both space and time. For weak gravitational fields like Earth's, the metric looks approximately like flat space-time with small corrections. The time component of the metric is affected by a term proportional to the gravitational potential. The space components are affected by a much smaller term. When you work out the geodesic equation, the equation that tells you how objects move, you'll find that the dominant contribution comes from the time component. Specifically, objects move in a way that's dominated by gradients in the rate of time flow. Where time flows faster, objects accelerate toward where time flows slower. This is gravity. Now let's think about orbits. Why does the moon orbit Earth? Why do planets orbit the sun? In Newton's picture, there's a gravitational force pulling the moon toward Earth. This force provides the centripetal acceleration needed to keep the moon in orbit. In Einstein's picture, there's no force. The moon is moving in a straight line through curved space-time, a geodesic. But because space-time is curved, that straight line in four-dimensional space-time looks like an ellipse in three-dimensional space. The moon is falling around Earth. And the reason it falls is primarily because of time curvature. The moon is trying to move through space-time on the straightest path possible, but time runs slower near Earth than far away. This gradient in the flow of time causes the moon's path to curve, to bend toward Earth. The moon is constantly falling toward Earth, but also moving sideways fast enough that it keeps missing. That's an orbit. Here's a thought experiment that makes this clearer. Imagine you're far from any gravitational source. You throw a ball, it moves in a straight line at constant velocity, no acceleration. Now imagine you're near a massive object like Earth. You throw the ball horizontally, it curves downward and hits the ground. Why did the path change? In Newton's theory, a force appeared. In Einstein's theory, space-time changed. The straight path through space-time is now different because time is curved. The ball is still following a geodesic, the straightest possible path. But the geometry of space-time has changed, so the geodesic looks curved to you, and the curvature is almost entirely due to the time component of the metric. Let me give you another way to think about this. Imagine space-time as a rubber sheet. Everyone uses this analogy, but they usually get it wrong. They show a heavy ball making a depression in the sheet and smaller objects rolling into the depression. But this analogy is misleading because it suggests space is curved and objects roll down a slope. That's not what's happening. The better analogy is to imagine time flowing at different rates at different heights on the sheet. At the bottom of the depression, clocks tick slowly. At the top, they tick fast. Now imagine an object moving across the sheet. It's trying to move in a straight line, but because time flows at different rates, the definition of straight changes. The object's path bends toward regions where time flows slower. This is gravity. Now let's talk about extreme cases. Black holes. Near a black hole, space-time curvature becomes extreme. Both space and time are severely warped. At the event horizon, the boundary of the black hole, time dilation becomes infinite. A clock at the horizon, from the perspective of a distant observer, stops completely. Time ceases to flow. If you watch an object fall toward a black hole, you see it slow down as it approaches the horizon, it redshifts, its clock appears to tick slower and slower. It never quite reaches the horizon from your perspective. It freezes there for eternity. This is time curvature taken to the extreme. From the perspective of the falling object, something very different happens. From their frame, time flows normally. They cross the horizon in finite time. They don't notice anything special at the horizon itself. They continue falling toward the singularity at the center. But because time is so severely curved, observers at different locations experience completely different flows of time. There is no universal now near a black hole. This connects to something profound about the nature of time itself. Time is not absolute. There is no cosmic clock ticking at the same rate everywhere. Different observers, depending on their motion and their position in gravitational fields, experience different flows of time. Your time and my time can run at different rates. And this is not just a matter of perception or measurement error. Time itself is different for different observers. This was the shocking conclusion of special relativity. And general relativity extends it. Not only does motion affect time through velocity-based time dilation, but gravity affects time through gravitational time dilation. The deeper you are in a gravitational field, the slower time flows. And this has been verified countless times. Muons created by cosmic rays in the upper atmosphere should decay before reaching the ground. But they don't, because time dilation extends their lifetimes. Particles and accelerators live longer than they should because they're moving fast and time slows down for them. Atomic clocks at different altitudes tick at different rates. GPS satellites compensate for time dilation. Gravitational redshift, the stretching of light as it climbs out of a gravitational field, has been measured. Every test confirms Einstein's prediction. Gravity bends time. Now let me tell you about something even stranger. Gravitational waves. When massive objects accelerate, they create ripples in space-time that propagate outward at the speed of light. These are gravitational waves. In 2015, LIGO detected gravitational waves from two black holes colliding 1.3 billion light-years away. What LIGO detected was not a signal traveling through space. It detected space and time themselves oscillating. As the gravitational wave passed through Earth, space-time stretched and compressed, distances changed, time intervals changed. The wave itself was a ripple in the fabric of reality. And because the wave affects time, detectors like LIGO measure changes in the light travel time between mirrors. The wave passes, time stretches and compresses, and we detect it. This is gravity as geometry in its purest form, not a force, not particles being exchanged, but the shape of space-time itself oscillating. Let me address something people often ask. If gravity is just curved space-time and not a force, why does it feel like a force? Why do you feel weight when you stand? The answer is that what you feel is not gravity. What you feel is the ground pushing up on you. Gravity, the curvature of space-time, is trying to make you follow a geodesic. That geodesic would take you toward the center of Earth. But the ground is in the way. The ground exerts an upward force on you, preventing you from following your natural geodesic path. That's what you feel as weight. The electromagnetic forces in the atoms of the ground are pushing against the atoms in your feet. If the ground weren't there, if you were in free fall, you'd feel weightless. Not because gravity disappeared, but because you'd be following a geodesic. Astronauts on the International Space Station feel weightless because they're in free fall around Earth. They're following geodesics through curved space-time. No forces act on them except for tiny air resistance and tidal effects. They're in the most natural state of motion. Free fall. This leads to Einstein's equivalence principle, the principle that started it all. In 1907, Einstein realized that if you're in a closed box with no windows, you can't tell the difference between being at rest in a gravitational field and being in a rocket accelerating through empty space. Both feel the same. Your feet press against the floor, objects fall when you drop them. This equivalence led Einstein to the insight that gravity is not a force. If it were, there would be a difference between acceleration and gravity, but there isn't. The reason is that gravity is the curvature of space-time, and acceleration also involves moving through space-time in a particular way. The equivalence principle is the starting point of general relativity, and it's been tested to incredible precision. No violation has ever been found. Now, let me tell you why all of this matters beyond just understanding gravity. The fact that gravity bends time means the universe has no universal clock. Different observers experience time differently. This affects everything: causality, simultaneity, the arrow of time, near a black hole, events that are simultaneous for one observer are not simultaneous for another. The order of events can change depending on the observer. This is not just relativity of simultaneity from special relativity. This is more severe. Gravity creates such extreme time distortion that the structure of causality itself becomes observer-dependent. And this raises deep questions about the nature of time. Is time fundamental or emergent? Does time flow, or is that an illusion? If different observers have different flows of time, what does it mean for time to pass? These are not just philosophical questions. They're questions physics must answer to fully understand reality. Some physicists, myself included, think time might be emergent. That at the most fundamental level, perhaps in quantum gravity, time doesn't exist. Only correlations between quantum degrees of freedom. Time emerges as a useful concept in certain limits. This is speculative. But the fact that gravity bends time, that time is not absolute, that the flow of time depends on where you are and how you're moving, all of this suggests time is not as fundamental as we intuitively think. And here's something truly strange. Inside a black hole, space and time swap roles. Outside the horizon, you can move freely in space, but you're forced to move forward in time. Inside the horizon, you're forced to move toward the singularity in what used to be space, and you can move in different directions in what used to be time. The singularity is not a place. It's a moment in time, an unavoidable future. Once you cross the horizon, reaching the singularity is as inevitable as tomorrow. You can't avoid it any more than you can avoid the next second. This is what it means for gravity to curve time so severely that time becomes space. Let me end with this. The reason you're sitting in your chair, the reason the Earth orbits the Sun, the reason galaxies hold together, all of this is because massive objects curve time. They warp the flow of time itself, and objects moving through regions of different time flow follow paths that curve towards slower time. This is gravity. Not a force reaching across space, but the geometry of space-time responding to mass and energy. After 50 years of thinking about general relativity, I still find this beautiful and profound. The universe is not a fixed stage with forces acting on it. The universe is geometry, dynamic, flexible geometry that responds to matter and energy by curving. And the curvature is primarily in time. Time runs slower near massive objects. And that gradient in the flow of time is what you experience as the pull of gravity. There is no pull. There's only curved time. That's what Einstein realized. That's what changed physics forever. and that's why gravity bends time. Thank you for watching. Welcome to General Relativity.